let's talk about isomerism in benzene. Okay, isomerism in benzene compound. So isomerism in benzene compounds. Previously in benzene, previously I explained to you about isomerism. All right, we have talked about stereoisomerism, we have talked about geometrical isomerism, the criteria and all that. And this is an extension. So let's say you are given benzene, all right, benzene compound. The position of the carbon in a benzene ring can be given numbering. So numberings can be allocated for each carbon in the benzene ring. So if we give numbering, then you can start with any carbon. You can start with this carbon as carbon 1, this carbon as carbon 1, any carbon you can start with. So let's start with the normal one, that's carbon 1. Okay, that's carbon 1, that's carbon 2, that's carbon 3, that's carbon 4, that's carbon 5, and that's carbon 6. Now, alternatively, you also have another naming system. Okay, all right. So that one uses the position as the location of a carbon atom is referred to as in ortho position. This is referring to the carbon in the ortho position. And then you have meta position, and then you have para position. All right. Now, ortho position, meta position, and para position. But this naming system is usually used for mono substituted, and di substituted, and so on. Okay. Then we use for mono substituted and di substituted. Okay, di substituted, and so on. Benzene compounds. Okay, benzene compounds we use for that. So when you have that, which I will discuss shortly, yeah, that's when we use the ortho, meta, and para. And ortho will be normally designated with O, meta will be N, and para will be P. All right. Okay. So you need to have this fundamental knowledge. This one, ortho, meta, para. When you're dealing with mono substituted. Is that a monosubstituted benzene? No, that's just a benzene compound. All right, that's all. Okay. So for this benzene compound, let's say you have chlorine. This is what we call a monosubstituted benzene. This is called a monosubstituted benzene, and this chlorine, all right, is called a substituent. It's called a substituent. And this position is given as position 1. All right, it has to carry position 1 because the numbering must start with the smallest number. So this is definitely number 1. So let's say if you have this structure, all right, and your chlorine happens to be here, that's where chlorine is. Therefore, now this becomes carbon 1. Where the chlorine is, it becomes the carbon 1. All right, okay. So if the chlorine is there, that becomes a carbon 1. This is called a monosubstituted benzene. Now, for monosubstituted benzene, this position is the ortho position, that position is the para position, and that position is the meta position. Okay, all right. So, and this is also the meta position. This is also the ortho position. Sorry, the ortho position. So we have ortho positions 2 sides, meta positions on 2 sides, and para position 1, because that's the other para position which has already been occupied. Okay. So if you have Cl, okay, Cl, and Cl, okay, you can call this, this can be labeled as 1,2-dichlorobenzene, okay, where you use the neighboring. Or you can also call it as orthochlorobenzene. Sorry. Okay, you can use this as ortho. So this is chlorobenzene. That means orthochlorobenzene. Okay, orthochlorobenzene, which normally you can see the complexity when ortho what we call ortho is be used in the naming system. It is a bit complex. It's a bit tedious. So we use numbering. Numberings are much easier. But auto meta para knowledge you need to know. All right, you need to know in order for you to refer to these positions. That means in the exam they can give auto positions, meta positions, para positions, or even sometimes for me to explain, I must say auto positions, para positions, and so on. Okay. All right. So I'm just highlighting that to you. So this one will be known as 1,2-dichlorobenzene. Benzene. Huh? All right. Okay. Rather than using auto and para. So I discourage you from using it. But you got to know what it is, as I said. All right. Okay. Now, isomerism in benzene for this structure. All right. So remember, I told you before, isomerism, okay, is either there is a structural difference in the compound, or if the structural difference is not, if the structural difference happen to be the same, then the orientation of the atoms within the molecule, orientation of atoms within the molecule will be different. All right, which makes the two structures which are considered as isomers to be non-superimposable. That means you can't superimpose one to another. The moment one molecule cannot be superimposed into another molecule which has the same molecular formula. That means both the molecules A and B happens to have the same molecular formula, but you can't superimpose on them. It only shows they have two different orientations of atom in the molecule. Although when you look at the structural formula, they happen to be the same. This is where you come across the geometrical isomerism, you come across the optical isomerism. We have already done, we have already passed that, so I'm not going to repeat that. I'm just giving you a gentle reminder. Now, here it is different. Here the isomerism is due to the positioning of the substituents. Due to the positioning of the substituents. This is why the substituents can also be positioned in this location. Okay. Okay, like that. This will be 1,3-dichlorobenzene. We've already done the naming, so you shouldn't have any problem. Huh? Okay. So the moment the names are different, that means the structure is different. So here it's very clear. All right, the structure is different. Okay, is that all? No, you have also this. Okay, this is 1,4-dichlorobenzene. Okay, 1,4-dichlorobenzene. This is 1,4-dichlorobenzene. That's what it is. 1,4-dichlorobenzene. All three of them are different structures, and therefore they are the isomers of each other because they share the same molecular formula. All right, so the structures are different. This is how structural isomerism occurs in benzene. Another point of view. Okay. Now, if you want to use the auto meta para, the monosubstituted name is what we call, we maintain it. So that will be a chlorobenzene. So this chloro has gone to the auto position. So it's auto chlorobenzene, right? So that is what it is, okay? All right, now this one was in the para position, okay? And this one is in the meta position, all right? This is the second substituent is in the meta position. The second substituent, this is considered the first substituent. Second substituent is in the para position. And the third substituent is in the auto position. So from the auto meta para, you can see they are in three different positions. And that is also a result of isomerism. Okay, all right. And therefore that results in isomerism. So this knowledge is important. Okay. Now there is another point to take note. Okay, there's another point to take note. Okay. All right. Now, whatever you want to take down, you can take down. Okay. I will give you 1 or 2 minutes for you to take down. And once you're okay, put a yes, and then I'll come back to you. We are looking at the location or position. Location or position of the second substituent. Okay. Second substituent in a monosubstituted benzene compound. So we are going to look at that. Okay, all right. Okay, what does that mean? So let's say you have what we call methyl benzene. This is methyl benzene. The common name for methyl benzene is toluene. So quite often toluene will be used in the exam as well. So you all supposed to know toluene is actually methyl benzene. All right, toluene is actually methyl benzene. All right. Okay, so this is methyl benzene. So this is what we call a monosubstituted benzene. And let's say your chlorine, okay, it reacts with chlorine. It reacts with chlorine. All right. So this chlorine, it can be any substance. So let me put generally X. Let me put generally X. Substance X. Okay, I don't want to put the X2. I just take it as a single atom. So this one is to be substituted into the benzene ring, which means one of the hydrogen here. Remember, which you don't see, there's a hydrogen atom here, hydrogen atom here, hydrogen atom here. So the X is going to substitute the hydrogen atom. So the moment X goes in, you got to highlight the X. That's the convention in chemistry. If you do not highlight, can you see you don't highlight anything here, that means it's hydrogen. That means it's hydrogen. The moment hydrogen has been substituted, another substance coming besides hydrogen, then you got to highlight that. Okay, then you got to highlight that. So, okay, so what we're going to look at it, all right, is when X substitutes hydrogen, is there a fixed position or location where X goes to? That means, is it that X can choose any one of these locations to go into and fit or link into benzene ring? That means it can either substitute this hydrogen atom, this or this, or is there a certain fix where it can only substitute this, cannot substitute this, it can only go to this position and not to any position? All right, that's the meaning of the title that I've given to you. So the point is here. What's your the type or the nature of your first substituent? The nature of the first substituent in a monosubstituted benzene will design, all right, will direct the second substituent, will direct the substituent to a certain fixed position. So that means this X cannot move into any position as it pleases. No. The position that it can occupy will be decided by the first substituent, will be decided by this. And therefore this has the power or the strength to direct this to fit into a certain fixed location. So it has. So first you have to know the first substituent will direct the second substituent to occupy a certain fixed position in the benzene ring. All right. The second point. Okay. The first substituent. All right. The first substituent can be classified. Generally, can be classified as electron donating group, atom, or electron donating group or electron donating atom, and electron withdrawing. So it is either electron withdrawing or electron donating. Now, if it is electron donating, it will direct the second substituent, second substituent to occupy either the auto or the para position. So that means there's a choice of two, either the auto or the para. But between auto and para, there is a preferred one. That means they do not occupy of equal probability. One is higher than the other. Later, I want you to think and come up which one. All right, we will put that into discussion. Then, if it is electron withdrawing group, okay, then the second substituent will be directed to occupy the meta position. Only one position. All right. So in this aspect, your CH3 is an electron donating group. Alkyl group is an electron donating group. Therefore, X will be directed to either occupy the auto, all right, or the para. You can also take this. This and this is the same. Whether it occupies here or here, same. So I'm only considering that. Okay. So which means there's a possibility of two products, not one product. So in the exam, that's what the examiner will test you. So you have your CH3, you have your CH3, all right? And then you have, okay, you have your, okay, as I said, your X, it can occupy this. This is one of the product. Or, remember, if this is only one, there's only one here, so it has to be an or. If you put A and B N, that means some of you put a plus, that means you're saying N, then you must have a two more. That means you must have two, and this also must be two. All right, be careful, what I'm trying to say. So CH3, all right, it can do this. These are the two possible products. Okay, two possible products because it's electron donating. It's electron donating. All right. Okay. Now earlier I told you, although both are in the exam, both are correct answers. You must give both, otherwise you lose 1 mark. But between them, one is favored more than the other. So can anybody tell me which one? Which one is favored? The auto or the para? Which one is favored? That means they're not of equal probability. So which one is favored? A or B? Auto or para? Which one is favored? Auto position or para position? What's your take? The auto position. So why do you choose the auto position? Why do you say the auto position is favored and not the para position? What's the reason? Remember, I've always told you, for everything there must be a reason. All right? Okay, of course you have to have your instincts, but there's also must be a reason. Okay, because you're saying closer to the methyl group. All right, okay. On the contrary, it's the other way around. All right, on the contrary, it's the other way around. So remember, this is the preferred one. This structure is the preferred structure. Between the two, that's the preferred structure. Now, why? In chemistry, there is such thing called steric hindrance. All right, due to steric hindrance, it's due to this. Steric hindrance is spatial hindrance. Molecules do not like to occupy spaces where the space is limited, the space is crowded, all right? Because sometimes that can cause extra repulsion. So they like to occupy where there is a bigger space for them to orientate themselves. So you can see between O2 and the methyl group, so the space here is very small, a bit limited, whereas from here to here, the space is large. So para will be favored more than the O2 and then the O2 position. All right, and this due to spatial constraint. Due to spatial constraint, spatial constraint in chemistry is what we call steric hindrance. Okay, all right. Now, electron withdrawing group. Okay, so let me give you an electron withdrawing group. So this is one example. That's your electron donating group. So I'm going to go for another example. Let's say we go for nitrobenzene. This is nitrobenzene. All right, nitrobenzene. Okay, plus X. So what are the possible products? So you should recognize nitro group as electron withdrawing group. Okay, as electron withdrawing group. You should see it as electron withdrawing group. So electron withdrawing group will direct your second substituent to occupy the meta position. And therefore the product that is expected will be, the product that is expected is NO2. Remember, these are very important points in the exam. You must be aware of this monosubstituted compound and disubstituted compound. So this time your X will occupy that. That's the answer. And there's only one product. There's no two products. Okay. Whereas for electron donating, it gives you two different products. Okay. All right. My next question to you is why? Why does your electron donating group, simple chemistry, we do not want bombastic chemistry, we want simple chemistry. Why electron donating group directs the second substituent? You see, the nature of the second substituent is not important. Well, that is why earlier I gave you chlorine, and then from chlorine I switched to X, because the nature of this is not important. It's the nature of the first substituent that's important. All right. So why is it directing this to occupy the O2 and para? Okay. Why is this electron withdrawing group directing the same X to occupy the meta? Now, the reason is electron donating group will practically have the tendency to donate whatever electrons that it's sharing, to donate it to the benzene ring. When you say donate it to the benzene ring, doesn't mean that it completely loses. No, it's not that. It's just a concept of displacement. All right. So, in other words, the effect of this electron donating group will increase the electron density of the benzene ring. So, increases electron density of benzene ring. Then electron density of benzene ring. It increases that, the delocalized electron. So when that is increased, as I said, simplified idea, auto and para positions are activated. So when auto and para positions are activated, and these are electrophiles, the one that goes after the benzene ring, already I told you in your foundation class, these are electrophiles. Okay, these are basically electrophiles. The one that attack the benzene ring are electrophiles. So the electrophile, so that means the auto position is activated, para position is activated, so they go after the auto and para. And because of steric hindrance, they prefer the para compared to the auto. Now, in the case of electron withdrawing, they decrease electron density of the benzene ring. They decrease the electron density of benzene ring, and therefore deactivating the auto and para position. That means it deactivates the auto and para positions. So when auto and para positions are deactivated, all right, the only position left is M. Deactivated means they don't go after that. So the only position is M, therefore X goes after the M. Or indirectly or technically, you can see the meta is activated. All right, meta is activated. That's a simple explanation behind why this happens. Now, another one is an exception. All right, now chlorine. Let's say you have chlorine. Okay, that means this is chlorobenzene. So chlorine, you all know, is a halogen. Therefore, it's an electron withdrawing group. That means it's an electron withdrawing atom. So if X, which is electrophile, substitutes one of the hydrogen of the benzene ring, the chlorine will direct the X, because it's electron withdrawing, it should direct the X to the meta position. But no, it doesn't. Halogens are exception, meaning though the electron withdrawing, they somehow or other activate the auto and para position and direct the X to occupy the auto and para position rather than the meta position. So this is the product and not the other way around. Okay, so I have come up with a more simple idea for my students. I've come up with a simple idea. So this is what I want you to use. All right, I want you to use this idea. What idea am I talking about? Look at the first substituent. You no need to categorize it as electron donating, electron withdrawing. All you have to do is find out whether there is a single bond, all single bonds, or all double bonds. Sorry, all single bonds or a presence of at least a double bond, not carbon-carbon. Okay, can be any, like carbon and oxygen double bond. The moment there's a double bond present, then it will be meta-directed. If only single bonds are present in the first substituent, again, it's the first substituent that you should analyze, because that's the decider. You look at the first substituent, if it's only single bonds are present, it is auto and para. Double bond present, it is meta. So let's look at it again. Look at this. So in this substituent, it is C, H, 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 all single bonds. So it has to be auto and para directed. No need this idea. But this is a chemistry. You have to know this idea. I'm just simplifying the idea. What I'm giving here is simplification. Whereas your chemistry is the one that dictates and explains why it's like that. So you have to know your chemistry, that you cannot let go. That's why always learn things properly. What you should do, then simplify your idea, not the other way around. Okay, now you look at this. You all have done your Lewis structures and all that. You should know there's a double bond between nitrogen and oxygen. There's a double bond. So since there's a double bond present, it will be directed to the meta. So in that case, you can look at chlorine. You don't need to know whether it's electron withdrawing. Chlorine only a single bond. So presence of single bond, it's auto and para. This will never fail you. You'll be okay with that. So remember that simplification which I gave you. All right, I'm not okay. So I'm not putting that in the notes. So you yourself write down. Okay, if the first substituent has only single bonds present, first substituent has only single bonds present, the second substituent will be directed to occupy auto and para position. The second substituent will be directed to occupy auto and para position. On the contrary, if the first substituent has a double bond present, then the second substituent will be directed to occupy the meta position. All right, take down whatever you have there.